little bit about Current, first of all. This is the second of our series webinar, and Current is an organization that represents innovation network innovation companies in Europe, the voice of European innovation network companies. And really, we're focused on optimizing grids, bringing new technology to grids, and not just optimizing existing grids and getting the most of them, but new grids and developing grids for tomorrow. That's the business we're in, and we're very focused on the Green Deal. And we believe that the network, the power network, is absolutely central to achieving the Green Deal in Europe. So we're very committed to that. Next slide, please. So this is the previous webinar hosted on optimizing power grids for a clean and greener future. That was hosted by Smart Wires in October. Next slide, please. So a little bit about me. I'm Vice Chair of Current and Chief Executive of SuperNode. And SuperNode is a company that develops the housing for superconductors to help with the thermal management. And that's really about expanding the use case. So superconductors are in use today, but in limited circumstance in major cities. And we're working to improve the thermal management so that they work reliably 24/7 and effectively that the superconductors remain super and cool. And one of the applications we're really focused on is the offshore. So bringing those remote renewables, more of them, more economically to markets. So we're delighted to have achieved a statement of feasibility for an offshore, and we're really focused on extending the range and application of this fantastic product. Next slide, please.
Thanks a lot for having me. It's a pleasure to address your conference today and say a few words by way of introduction on the offshore strategy, which I assume most of you will will know at this stage. But I'll take the opportunity to walk you, but I'll try to be really quick, through a couple of the main points we have raised to set the scene. And I would just like to apologize in advance that I won't be able to stay for the panel discussion in the very end. But I look forward to hearing the outcomes of the conference. So I think we can move directly to the next slide. First of all, why did we decide to do a specific offshore strategy? Because surely offshore renewables is only one part of our effort to reach net zero in mid-century. Clearly because we identified the strategy on the side of offshore renewables as being a particularly steep one, if you like, simply, first of all, because of the steepness of the increase that will be needed looking at offshore renewable energy. Because what we have today in the waters with 12 gigawatt mainly in the North Sea is of course rather limited compared to the contribution that we consider and our models result in as necessary for offshore renewables to grow in 2030 excuse me, and in 2050, which as you all know by now goes up to 300 giga for wind and the potential additional 40 gigawatt for ocean energy technologies. This is really just to show why this broad portfolio of technologies is so important, because we're speaking, if we look at the North Sea, which is really where efforts so far have concentrated, we're speaking about an environment which is relatively specific and I would say even unique in an EU offshore context, because it is so shallow. That is to a certain extent still the case in the Baltic Sea, but much less so in the other sea basins that we have, the Atlantic, the Mediterranean, and the Black Sea. And all of those have a potential, but they require different technologies. And we want to tap into all of those. What are the key objectives of the strategy? I would name four, perhaps. First of all, the targets in themselves are important because they set a clear direction, and they are important as a sort of orientation mark for the industry in terms of what is expected of industry, in terms of the capacities which will be needed. Secondly, then based on that, to encourage public and private investment in new infrastructure and also research, both of which very important in the context of this seminar. Clearly, as I said earlier on, the need for regions to work together more efficiently and more closely, and we want to set the frame for that, and perhaps offer the right forums to do that. And lastly, for that investment to come forward, what is needed clearly is a clear and stable legal framework, which gives investors the kind of certainty and perspective that they need.
Our next speaker is Arnoldus van Wingerde from the Fraunhofer Institute for Wind Energy Systems, the Chief Scientist. Over to you, Arno.
Yep. Hello, and welcome from me as well. Happy to be here. And I wanted to give a small presentation on energy in 2050, seen from the 2050 point of view. Next. Okay, since I'm from wind energy, I'll talk a little bit. Since I've been in wind energy turbines have been growing from 55 kilowatts with about 10-meter long blades up to the 12 megawatt Haliade, which has blades which are over 100 meters high. And as you can see, to the buildings in the background is starting to give some competition to the Eiffel Tower already. So we're getting a North Sea full of Eiffel Towers. Next. And not just the size of the individual turbines have been growing, wind energy as a whole has been growing quite nicely as well, up to about 500 gigawatts. In the insert, you can see the offshore energy, which is following a similar trajectory. It's just that it's like maybe some 20 years behind. Next. So this is all very good, and this is typically the point where I congratulate the industry on a job well done. And then, okay, where do we need to go? Next, let me zoom in here. So next. So we've done 500 gigawatts, but we need to do about 18 terawatts. And that's a different number than Joachim mentioned, the previous speaker, because I'm looking actually at the energy needed in the whole world. And then let me show you a kind of reversed Gantt chart. And this is also useful for slapping politicians around the ears with the actual need for not just talking about it, but actually doing something. So we need to be ready by 2050. Everybody agreed on that part. Which means, you know, you will be digging in the 10 years before that, and hopefully starting a little bit earlier than that, which means that you got a legal framework in place before that. You need to get the planning in place for that. And you need to work really hard on the research if you want to talk about types of grid just about right now. One thing on the cost development that we also may be neglected. Materials may run out or become more expensive if we are simply starting to dig out the whole world for, well, for instance, making this 10,000 Eiffel Towers in the North Sea. But on the other hand, we can now go chuck, 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 like T-Ford style, have automated production technology for those wind turbines. And that would probably also help. And I see similar advantages of scale in other fields, but it's a very, very major task. Next slide. And talking about national grids, I mean, this is from The Guardian, you know, a plan to couple the largest solar park in the world to be built in Australia with Singapore. And I mean, that looks like quite a distance. Next. Putting actually the map of Europe in more or less the same scale on top of that will show you how big that really is. And it's also showing how possible and necessary it will be to couple everybody on the planet together in order to get this thing actually working.
So with renewables, we will see and have seen that already, geographical concentrations of generation. We will see a need for longer distances in transmission, and I would like to add even the highly distributed resources, such as, if I go to the extreme, rooftop solar, will generate local peaks, which will need to be distributed over longer distances in order to benefit from complementary weather situations and to provide some flexibility or balancing for load and generation. And there's another driver. If we talk about offshore, then we need to talk about cables. And here, remember, longer cables were not very compatible with high transmission capacities. But in future, we are talking about developing a sort of an overlay network, a meshed infrastructure. And that means this will be built much more like a network where you don't build individual lines, you build nodes and connect them with lines. And all this coming from different vendors. So all the components have to become much more interoperable. And a certain level of standardization will also be needed in order to allow us to build a grid step by step, because obviously nobody will order a grid in one big project. So that is what we have to learn and to develop in time.
Thank you, Jochen. Thank you for that. And I think what's interesting there is the call to arms and talk about a moonshot. So we have reverse Gantt charts and now a moonshot. And I also want to acknowledge the great work, Jochen, and the inspiration that we took in our company from Best Paths, because they demonstrated they did a type test for a superconducting cable that could move beyond 3 gigawatts and more to come. So there's hope. So our next speaker is Cornelis Plet, who is responsible and involved for many years with the promotion project.
Thank you, John. Also, thank you for the invitation to speak here. So, from the previous presentations, the need for DC grids, I think, is quite clear. And what also is shown by the previous presentations is that the scale that justifies HVDC really also requires international collaboration. So, what are then meshed DC grids, and what can they do for us? Next slide, please. So what you see now is a map of all the currently planned and in operation HVDC links in Europe. What you can see is that these are all predominantly point-to-point, single purpose, and what you can't see from the map, but is the case, is single vendor projects. And yeah, you can see that it's already becoming quite spaghetti. Many links are in place, but it's not yet possible to make a grid out of this, because as indicated by the different colors, these lines don't have different voltages, they have different voltages and also different converter configurations. The first sign of the hybrid transmission systems are really already coming into place. So the blue lines, for example, the Caithness-Moray, which is an embedded HVDC link in Scotland, and at the bottom you can see the tip of the Ultranet link in Germany. But also hybrid interconnectors. So the two red lines, the top one is the wind connector and the bottom one is the Nautilus link, are already on the map. And these hybrid systems, they all happen to be multi-terminal, but not yet meshed. So what is the difference? Now, an alternative to this could be the radial multi-terminal system, which you see in the middle. And this could really serve the same transmission need. But what you can immediately see is that we need fewer converters for this. We combine the two links on the left-hand side and have one converter to go out. And this immediately leads, of course, to lower cost, a lower footprint, lower losses, and a higher availability of the system as a whole. And it allows us, as in the example of a hybrid interconnector, to combine the purposes and increase the utilization of the grid. It also comes with challenges, of course. For example, the coordination between the different projects, the different parts of this DC grid and their partners, and multi-vendor interoperability. Several of those types of grids have already been built and put into operation in China, which means that from a technical perspective, in the right setting, which is one country and one TSO, this can work. And in Europe, several examples are in development, like the Caithness-Moray Shetland extension, Ultranet, and Eurasia. The only problem is, though, that in case of a DC fault, there's no redundant path. And that is problematic for large HVDC system ratings when you go into the multi-gigawatt range. Because in that case, we might exceed the maximum loss of in-feed in the AC synchronous area that it is connected to. And one solution to this could be the meshed multi-terminal system, which is here on the right. Here we can reduce the impact of a DC fault on the AC system by rerouting power through a redundant path. This comes, of course, at the cost of having to have a DC grid protection in place, for example, the hybrid breakers or even hybrid converters, and the need for an additional cable and cable capacity. It is technically possible. In China, they are commissioning at the moment such a grid. But the real benefit of such a grid comes in cross-border, large-scale settings in which it combines different purposes. And that's really hard to achieve in international settings. It requires a very strong international collaboration and political commitment, and multi-vendor interoperability, which could, of course, be helped by a DC system grid code. And two challenges that we have in the EU in realizing this is, on the one hand, the number of cables and converters that we need to build. So it is always a good idea to minimize the amount of cable necessary in a transmission grid in order to minimize the cost and environmental and societal impact. So therefore, it's good to cluster wind farms to hubs and then use the highest possible cable rating to go to shore. In the EU, we have an offshore wind target of 300 gigawatts. And on top of that, you have to add also interconnection targets. And if you then look at the state-of-the-art HVDC cable ratings, which is inching towards 3 gigawatts, you can see that we need hundreds of cable corridors and also hundreds of associated onshore converter stations. Now, in order to minimize the impact on the surrounding countries in the Netherlands, it is really important that we work towards having higher capacity cables and smaller converters. And the question is, of course, what can we do to do so? Could we, for example, go to a lower voltage transmission grid with superconducting cables and converters based on silicon carbide technology?
I want to start with some words about the Best Path project, which was already mentioned by Jochen Kreusel. And I just want to highlight two topics out of the Best Path project. It says gigawatt scale superconducting cables are technical, mature, and cost competitive for high power transmission. And cost competitive means here total cost of ownership. And the recommendation for policy is to allow feasibility studies and public tenders and incentives for the deployment of this technology in the grids. And I think that is one of the important messages out of Best Path. We are coming now to our vision, and we want to marry high currents with medium voltage to reach high power MVDC, and that is the situation where we are looking for. And we are coming here to a possibility of multiple gigawatt. If you see here the medium voltage source converters, you easily can imagine that with a level of plus minus 40 kV, we can reach easily with 50 kiloamps, 5 gigawatt. And that is the range we are looking for, even going up to 10 gigawatt. And that with the same or lower CapEx and definitely lower OpEx compared to cable systems.
So our next speaker is Dirk van Hertem, professor from Leuven. And over to you, Dirk. And we have another questionnaire as well. So over to you, Dirk.
Yeah, thank you very much for the opportunity to speak. I will be quick. I also have too many slides. My apologies for that. There are also many animations. We'll see how it goes. I'll try to bring my messages over. Next slide, please. So, yeah, we have ambitious goals. This has been mentioned before. We would like to have 450 gigawatt of offshore wind by 2050. Some say it's only 300 gigawatts. So 450, 300 doesn't really matter. It's an enormous amount. And if you go to the next slide or the next animation, if we look into that, what Wind Europe says is that we would like to have 200 gigawatt in the North Sea. And just for fun, if we have 200 gigawatt in the North Sea and we have 5 gigawatt links, which is not current day practice, but about to double. Next. Can you push another time? Yeah, this would be more or less the number of lines that you would need to put in the system. Double the capacity, the maximum capacity that you have today. Clearly, this is going to look like spaghetti. This is not really a nice thing to do. So next. What we actually will need is a DC grid, but not just to bring power to the shore, but also bring it inland. So really need to push power. We don't need it in the north of Norway. Nobody lives there. So we need to bring it to Europe. We need to bring it to Bavaria, where this BMW is made, which was mentioned earlier. So we will need a full upgrade of the system. And in my opinion, this upgrade is at least at the same level as the upgrades that were done in the 70s when we had to connect nuclear power and interconnect countries. We'll have a massive challenge ahead. And this is without onshore developments and solar developments, which are equally interesting. What are the technical hurdles? To be honest, well, yes, HVDC is ready, but to have the suitable ratings to really make it appropriate for really long distance offshore, when we talk about some gigawatts, that means that we also need to have the voltage levels available, and that's not that long. Only the first systems at 500 kV are being installed. 640 is kind of ready. 800, that's not yet really there. So there's really big power is still some developments necessary, but we're now in the ballpark where we want to be. It's kind of also not so super cheap, mainly the converter stations, which we inconveniently then have to put on a platform because you cannot really put them on the water, make them also very big and expensive investments. So that's also not really helping our development. They're large, complex, expensive. If we have such a system, control and protection is going to be more difficult, or complex interactions between AC and DC systems, interoperability is an issue, protection, and breakers were missing. So basically, we said for 10 years that we're ready, but only now we are really at the point that we're truly ready, I would say. But there are also two other things that limit our technical development, I would say, is that, well, it doesn't really match well with what we're doing today. It doesn't really fit with the existing system, and we don't really have the experience to deal with that. And it's not helped that we don't have existing installations in Europe. So I think that we will have DC grids in the future. We need them because otherwise we're not going to have our mass integration of renewables that we all want. The perceived risks and uncertainties have delayed current developments. We were ahead. I'm not so sure that we are. I have to say that the recent change with both TSOs and vendors make me hopeful that things could happen in the right direction. The required upgrade of the grid is fundamental. It's not a patchwork of solutions, and we cannot live with the "this is not how we do it today" mentality. This has to go. We are going to change everything and deal with it. Regulation should never be the blocking issue. If regulation is blocking progress, then it's bad regulation. I think we need to be fair and say that as well. AC and DC systems interact. Fine, there is more control, but there are adverse interactions possible. That means that we need new tools, and the operation of the hybrid AC-DC grid shall be different from the existing grid. So there are changes. And the slides that I skipped are the following. Let's start to build the DC grid today. There is a significant societal benefit, even under different scenarios. It's profitable to do it today. Doing this demo would reduce risk, and given the high payback period, probably this should be a public investment.
I'd like to thank the contributors today on the panel. There's some more webinars coming in 2021 from Current, accelerating the energy transition. The next one is how dynamic line ratings can help optimize the grid, and that's on the 14th of January. And thereafterwards in February or March, we'll have one on cybersecurity, which is going to be very, very important as we move towards more solid state devices and controllable passive, move away from passive networks to more active networks. It's going to be crucial that we cover cybersecurity to keep the lights on. So thank you very much to all the presenters, and thank you for your commitment and slides. I wish we had more time, but we can only touch on it, and we may be back to you to help us answer some of these questions we have coming in, and we'll do that offline. So thank you very much to everybody, and thank you for joining us.